Today we're going to wrap up describing quantitative data with numbers with some more learning targets. So today, what we're talking about, I can calculate and interpret measures of spread, range, interquartile range, and standard deviation. I can identify outliers using the 1.5 times IQR rule. I can construct and interpret a box plot. I can use appropriate graphs and numerical summaries to compare distributions of quantitative data. All right, so first, standard deviation. So there's two main ways of measuring spread, standard deviation and interquartile range. Today we're going to touch on both of those. Beginning with standard deviation. So it measures the average distance of an observation from their mean. It's calculated by finding the average of the squared distances, then taking the square root. This average squared distance is called the variance. All right, so basically variance is before you square root to find the standard deviation, okay? Now, this formula is in your packet. Now, the only thing is you really won't ever have to use the formula, okay? In all the AP tests that I've searched through, I've never come across an instance that you had to use the formula to calculate the standard deviation. So more of the focus of this is going to be, can you find it using the calculator? Okay, so again, when you're given data and we want to do calculations with it, I'm going to make a list out of the data. Okay, so I'm going to go into stat. Now I already have a list here that I need for later, so I'm going to type mine into list 2. You put it into whatever list you have available. All right. So, typed in my values. Now, if I want the standard deviation of this, again, I'm doing a calculation of a one variable statistic. So I'm going to do one variable stat. Now this time for me though, I have the data in list 2. So if you ever input your data into a different list, simply make sure that you're commanding the calculator to read the proper list for you. Okay? In this case, list 2, and calculate. All right, the standard deviation that we're looking for right now is going to be this SX value. Okay, SX is going to be our standard deviation. So we're calculating it to be about 2.52. So what does that mean though? Okay, what is that telling us? Well, what it's telling us is that the average distance each foot length is from the mean is approximately 2.52 centimeters, okay? Because we were talking about foot lengths of 7 14-year-olds from a sample, all right? So when it comes to describing standard deviation, I want you to memorize that because it does come up where they ask you to interpret standard deviation. Well, when you calculate it, that's what it means. The average distance each observation, so whatever your specific type of observation is away or is from the mean is approximately blank, and then include the units, okay? So memorize that structure, all right? So that's going to be how you always answer if they ask you to interpret standard deviation. That's what it is. It's the average distance each observation is from the mean, okay? Know that. Highlight it, star it, do whatever you need to, but you need to know that. Now, caution though, standard deviation, like the mean, is affected by outliers. So it should not be used when you're dealing with heavily skewed data, okay? It won't exactly be useful if your data is skewed. All right, now let's look at comparing standard deviations. So when I'm looking at data, getting an approximate idea of what does standard deviation look like. Standard deviation, again, is a measure of spread. So the more spread out something is, it means it has a larger standard deviation. The more compact it is around its mean, that means it's going to have a smaller standard deviation. So when I'm looking at these two machines, machine A and machine B, both have a center at 3. But notice machine B has a lot of values at 3, and then the other values are relatively close by. Machine A only has a couple at 3, and they're more spread out. So what this means is that the standard deviation of A is going to be greater than the standard deviation of B. So when you're looking at dot plots, some leaf plots, whatever, you should be able to get a rough estimate if you're comparing which one would have a greater or smaller standard deviation. Again, really all it comes down to is how spread out is the stuff that you're talking about, okay? The larger the spread, the greater the standard deviation. Now, remember my little caveat is I said standard deviation should not be used with heavily skewed data, okay? So when the data is skewed, we're going to need something else. So we're going to use what's called interquartile range to measure the spread, okay? So here we're going to introduce quite a bit of new vocabulary. Now, the thing to keep in mind though is in order to do these by hand, they need to be in order. So I'm going to have to rearrange these. So 20, 22, 24, 24, 25, 28. Okay, so it's the same values as before. I'm just kind of putting them in order so I can do this by hand. So again, if you're dealing with skewed data, this is what you should do. Okay, these are the measures you should use instead. I'm going to quickly show you by hand, and then I will show you how to do it using the calculator. Okay, so looking at these. So you should be able to find the median, all right? So the median is going to be the exact center of the data. Okay, so here we have 7 data points. So the median is going to be the middle of that. Okay? No. Oh, I'm sorry. I thought we were still dealing with 7. I'm missing, oh, that's where I went wrong. I am missing a 25 here. Okay, so the 24 is right. I was just missing that value of 25. All right, so quartile 1. So quartile 1 is now, I'm splitting the data in half. Okay, so I'm not using the median anymore in these following computations. Okay, so I'm looking at taking out the median. Now my data is cut exactly in half. The lower quartile is basically the median of the bottom. So the exact middle of the bottom. Okay, so in this case, there's only 3 values under the median, so it's the middle one. And then up top, we get 25. All right, so again, the quartiles, quartile 1 is a cutoff of the bottom 25%. Median is a cutoff of the bottom 50%. The third quartile is the cutoff for the top 25%. Okay, so basically what I've done is I've cut my data into equal 25%, equal quarters. Okay, the interquartile range. The interquartile range is just Q1 minus, or sorry, Q3 minus Q1. So just like standard deviation, it is a measure of spread, okay? It just is a measure of spread that's useful when you're talking about skewed data. Because when dealing with medians and quartiles, you're kind of alleviating yourself of being influenced by outliers. All right, so there's some new vocabulary for you. The quartiles, median, and now the interquartile range. Now, we can use this to determine if there's any outliers, okay? So this 1.5 times the interquartile range, that is going to create a window, okay? And it's going to help us determine if there's any outliers, okay? So for that data, so 1.5 times the interquartile range, which we said is 3, is 4.5. Okay? So what we're going to do is we're going to take Q1 and we're going to subtract off that 4.5. And Q1, sorry, I forget what it was already. Q1 was 22. So 22 minus 4.5 is going to be 17.5. So what that's telling me is I take quartile 1, I subtract off the 1.5 interquartile range, and what that's giving me is a lower bound. Anything that is smaller than 17.5 would be considered an outlier. It's too far away from that quartile. Same thing up top. So here I'm going to take the third quartile and add on that 4.5. Oh, sorry, wrong way. So the third quartile is 25. So 25 plus 4.5. So again, this would be saying it's too far above that third quartile. So anything greater than 29.5 would be considered an outlier. Okay? Now, the nice thing is neither one of these are creating any outliers, because if you look here, our biggest is 28, which is within our appropriate window, and the smallest is 20. So here that's showing us that we don't actually have any outliers in this data, okay? We're within the appropriate window. That's what that 1.5 times the interquartile range is doing, is creating a window of what would be reasonable to expect for data. Anything outside of that is a potential outlier, okay? So now we're going to use the 5-number summary to make a box plot. Now the nice thing is I know you're being thrown a ton of stuff today. Luckily the 5-number summary is everything you've already been doing. Okay? So the 5-number summary, all it is these 5 values which we've already calculated. Okay? So that's going to be the nice thing is we've already done all the brunt work for this. Now we're just going to turn that 5-number summary into what's called a box plot. Okay, that's going to be the final typographical display that we learn in this chapter. So, for a box plot, so 20, 21, 22, 23, 24, 25, 26, 27. So to make a box plot, I'm going to lay out from my lowest to my highest value, okay? Just like a dot plot would. Now I'm going to mark each of those points, okay? So my minimum value was 20. My first quartile was 22. That one I'm going to mark with a bar. My median is at 24. Third quartile is at 25. maximum at 28. So when it's a min and max, I put dots for. All the others, I put bars for. That is how you make your box and whisker plot. Okay. So again, as long as you know the 5-number summary and it's everything we've already been doing, it's actually really easy to make a box and whisker plot. Now, what this is telling me, okay, it's telling me 25% of my data is in that upper stretch. 25% of my data is in that portion of the box. 25% of the data is in there, and 25% of the data is in there. Is breaking it up into equal fourths. So having a bigger span isn't meaning there's more data in there. All it means is that the data is more spread out in there. Okay? So that is a key concept I need you to know with box plots, is having a longer stretch in there is not saying there's more data. It's exactly the same amount of data as everywhere else. It just means it's more spread out. Now, let's talk about, we just did this by hand, so let's talk about how to do this on the calculator, okay? Because again, that's going to be key, is efficiency. Can we get the calculator to do a bunch of work for us? All right, so to the calculator, whenever we are given a set of data, we want to put it in a list. Okay, so that's the list one that I already had pre-made, because again, I didn't want to make you sit here and watch me by hand do it. Okay, so my list one is all of that stuff. Now, the cool thing is I can now go in and I can find the 5-number summary. Okay, so I'm going to calculate the 5-number summary. Now here my data is in list 1, so I'm going to switch it back to list 1. And in that same one variable stat, notice when I scroll down here, notice right here at the bottom, there is my 5-number summary. Okay, it has everything there already for me. So that's a really quick way. If you need a 5-number summary, you can just type in the values to the calculator and make a list out of it if you don't want to have to do it all by hand. Okay, so again, just knowing the efficiency of the calculator. So this one variable stat is useful for mean, standard deviation, 5-number summary. The only thing I can't find is the interquartile range, but how easy is it once you have this? If you need IQR, all you have to do is take 44 minus 26. Okay, so even doing interquartile range is easy. It's just the only thing that's not explicitly shown on the calculator. Now, your calculator can also make a box plot for you, okay? So whenever you're doing a graphical display, just like when I showed you how to do histograms, whenever you do that, it's in stat plot. So second, y equals, to get into the stat plot menu, go into the first one. I need to turn it on. Now this time I want a box plot. Okay, that's going to be this one. Notice there's two different commands here for box plots. I prefer this one because this one is going to show outliers for me. Notice it has those little dots on the end. This one, if there are outliers, using that 1.5 times the IQR formula, it'll actually remove those outliers and just put a dot there instead of connecting it to the whisker, okay? So awesome feature there. That is also a really easy way to tell if there's outliers because it'll do that computation for you, okay? So my X list is in list 1, so I'm ready to zoom stat. So zoom 9, and there we go, okay? So that's we can get the calculator to make a box and whisker plot for us. Now, again, on the AP test, if you're ever copying this down, make sure you also copy down the scale. They won't give you credit just for sketching that. You do need to make sure that you put down what your scale is and all that kind of stuff as well. But it's a really quick way to see right now. I can already tell you there's no outliers because there's no dots sitting on the outside. Okay. So that's how I get the calculator to do it for you. One last thing. All right, so the states differ greatly in the kinds of severe weather that afflicts them. The histogram below shows the distribution of average annual property damage caused by tornadoes over the period from 1950 to 1999. When asked for summary statistics, Minitab produced the following output. Okay, so here I mentioned a histogram before. I removed the histogram because that's actually what I want us to make. Okay, so what I'm giving us is this Minitab output. The AP test is very much known for giving these Minitab outputs. So it'll give you data and it wants to know, do you know what to do with it? All right. So first thing, what is the shape of this distribution? All right, so by shape, what is it talking about? Well, remember we talked about how to determine the shape, okay, based on comparing the mean to the median. All right, so if I look here, the mean is sitting at 22.39, while the median is only at 12.66. So what is that communicating to me? Well, it's communicating to me that the mean is being pulled up. Okay, so the mean is being pulled up because the median is back here somewhere. Okay, and remember the tail is what pulls the mean. So basically what I'm trying to convince you of is our shape. It's going to be something where the mean is being pulled up. The shape is going to be skewed right. So get into habit of finding little tricks like that. You can determine an approximate shape just by comparing the mean and the median. Because the mean is so much greater, it's telling me that's where the tail is. Okay, so the tail is off to the right. So we could say right away, even without looking at this, it's going to be skewed to the right. What else? All right, well, I can actually make a box plot just by looking at this data. Okay, now you may be wondering, how can we possibly do that? Well, I have my 5-number summary, right? I have my minimum, Q1, median, Q3, and maximum. So I have everything that I need to make my box plot here. So 0, 10, 20, 30, 40, 50, 60, 70, 80. So notice I'm just counting by 10 because I have to span all the way from 0 up to, whoops, I need to be closer to 90. So here counting by tens feels appropriate just because I have a big span of numbers to go from. My minimum is at 0. My Q1 is at 2, so like way down there. Median is at about 12. Q3 is up at 41. Maximum is way up here at almost 90. So the cool thing is with a Minitab output, it gives me the 5 numbers that I need in order to make my box plot. So it's really easy to sketch that box plot for me. And again, recognizing 25% of my data is there, which is really spread out. 25% of my data is there, relatively spread out. 25% in there, and then still, even in that itty bitty little sector, 25%. So what that's showing me, pretty much, is we have very condensed data in the lower values spread out up top. That is another convincing thing to show me that this is likely skewed to the right. Because if you look at how spread out the top is, how condensed the bottom is, how compact that data is. All right, so now we can ask some questions about what percent of the data is between what values. So here we're talking about the 50 states and the amount of damage that they're given. Well, what percent of states had between 2.23 million and 88.6 million in tornado damage? So that's asking from here up to up to the maximum. Okay? Well, each sector, so that's going from this sector through that sector all the way up here. Well, to me, that looks like 75% of the data is going to be between those values. It's covering all of this, all of that, all of that. So that's going to be 75% of the states are going to have between that much data, because it's encompassing 3 sectors of the box. 2.23 million to 41.63. So that's covering from here and there. So that's covering 2 sectors of my box. So what that's telling me is 25% of my data is in there. So that's another thing you should be able to do, is a recognition that the percent of the data, well, when it's broken down equally into 25%, you can tell me what percent of the data is between certain values if they correspond to quartile 1, quartile 3, the median, the min, the max, anything like that. All right? So, just to wrap up, the median and interquartile range are usually better than mean and standard deviation for describing a skewed distribution or distribution with outliers. Use mean and standard deviation only for reasonably symmetric distributions that don't have outliers. And another note, numerical summaries do not fully describe the shape of the distribution. You always want to plot your data as well to look at the distribution. All right. So I realize that has a lot of information. So again, just like last time, if you found anything confusing, please just make a note of it and then ask me in class when you're back to do some more explaining on that concept.